All right, hi. Welcome back to Math 234. Last couple of days of class, we're going to spend the time reviewing for the final. Since at this point you've learned everything that you need to know, we've made it through the course. Now we just have to make sure that we remember all of it for the exam that's on Monday. So, this video, to now say a second to the thing over the computer that's over there, this video is being recorded in the fall semester of 2025. So this information will be specifically for that semester, though if you're watching this at a later date, I'm sure you can find some other information about what's specific to you. But back to real time. What do we have going on for us? The post-course survey is available now. It's on D2L. You can see the announcement right there. It's a two-part survey. The survey itself is anonymous, which means we cannot tie it to your grade. So you take the survey, it has a secret answer hidden somewhere in there. If you've taken it, you know it already. So you just have to take that secret answer that you find during the survey and use it to answer the actual quiz for the bonus point. It's not a real question. It's just you'll see it when you get there. Very simple. You just have to take the survey to find the answer. Again, that's worth half a credit or half a percent of bonus credit, extra credit, however you want to think about it. We just tack that on at the end of to your grade at the end of the semester. The other thing worth talking about right now is some information about the final exam. Again, we take it on Monday at 10 a.m. It will not be in any of your regular classrooms because finals week is always a different schedule for every course. So just all the old rules stop applying this Friday or after this Friday, I guess, to be technical. So starting Monday, completely different schedule. You should check the MSU SIS website to figure out where your final is located. Because again, it'll be different for most sections. Alternatively, if you go to recitation tomorrow, which you should go to because we have our final weekly review, and they'll also be reviewing for the final. But if you go to recitation tomorrow, your recitation instructor should tell you specifically what room you're going to. Because by the time you get to your individual sections, then you stay grouped together from there. So again, the final exam schedule is a little bit different from normal, so make sure you know what you're doing next week. Again, we take our final at 10 a.m. and it goes till noon. Other things worth pointing out, there are a few resources that we have for preparing for the final. There's another D2L practice exam that has been, I mean, we've had a D2L practice exam for every exam so far, but we also have a practice final that is just a PDF document. It's what we're about to go over right now. And it's written this semester to match the style, the format, and the length of the actual final. So if you pay attention to that, again, the written version, that PDF, one that we're going to do in a moment, that should match up with our final exam fairly well. Cool. So I don't see any questions on those topics. Figured I would have gotten one by now if there was going to be one. So let's move on to the math part, which means I don't need the internet browser anymore. And instead, I want to bring this open. But also I should take it over to, yeah, this spot. Okay, a little bit unconventionally, I'm going to start with the back half of the practice exam because I think it kind of makes sense to start there. One of the things that I want to just give you a heads up for on the final exam. It's this page that we keep talking about and have been talking about pretty much every day since exam 3. We have a few different versions of the fundamental theorem of calculus, right? The original fundamental theorem is what you learned in Calc 1, but then we also had the fundamental theorem for line integrals, Green's theorem, Stokes' theorem, and the divergence theorem. All of those are methods for integration. And thus far, when you've been needing to use one of them, it's been within the section where it's like, hey, we're going to use Stokes' theorem to solve every problem that's in this homework set. Then you move on to the divergence theorem. It's like, let's use the divergence theorem to solve every problem in this set. On the final exam, we are just going to throw about 4 or 5 integral questions at you and say nothing else about how to solve the problem. So part of what you'll need to recognize on the final is which of these formulas to use. Because again, it'll just say integrate this thing, and there's going to be 4 problems, 4 or 5 problems in a row that are all, here's a bunch of integrals, kind of have at it. It'll be your first job, or the thing that you'll want to do first, is figure out which of these formulas apply, or even maybe a couple of others that aren't even on this page. We'll see in a minute, in order to evaluate the integral correctly. So again, a big part of the final is going to be recognizing when to use each of these theorems. Because there's probably going to be one from each of the theorems, would be my guess. I'm pretending like I don't know what's on the final as I say that. So today, we're just going to look at examples of different types of integrals and figure out which theorem we should apply. So that's why we're starting on the back half of the practice exam, because that's where all those problems are. And it also relates most strongly to what we've been doing recently. So I thought it was a good place to start. So here we go. The first problem, number 6 in the practice exam. We want to evaluate the integral, which is just this line integral of yx dot dr, where c is the arc of the unit circle going counterclockwise from pi over 4 to 3 pi over 4. So, as is often the case, I think a picture will help us out. I'm going to draw one. So here's a coordinate axis, or coordinate axes. I'll put the unit circle on here. Hey, look, a circle. Trying to do a slightly better job of centering it. And if I look at the 2 angles that we're going between, hey, don't be like that. So if I look at the 2 angles that we're going between, pi over 4, I think should be that angle. And 3 pi over 4, probably this angle. Looks close and let me try that one more time. There we go. That looks a little better. 3 pi over 4. Meaning the arc that we're after is this one. And we said we're going counterclockwise, so we'll be headed that direction. So that's our integration region. Notably, this thing is not a closed loop. Right, this is just an arc of the unit circle. It's just a segment, just a piece of that circle. Not a closed loop at all, which means a ton of the theorems we were just looking at won't apply. Right, so like Green's theorem is one that might spring to mind here, since we are in just 2 dimensions. But Green's theorem needs a closed loop in order to work. We also still want our positive orientation for whatever that loop might be, which this thing is going in what we'd usually consider a positive direction. But again, since it's not a closed loop, we'll just go back to our standard methods for solving line integrals. Nothing too special, at least nothing from that post-exam 3 content is going to apply to this one. So, since I know that I just kind of have to solve this line integral directly, I'm probably going to want a parameterization. So if we go make R of t be our parametric curve, it's just the unit circle, so that'll be cosine t sine t. Again, I know I want a parameterization because I have just a one-dimensional arc. They're just moving in one direction, so I only need one parameter in order to talk about it. And also, don't forget that if we are going to have a parameterization, we should include our bounds for that parameterization. Usually our default, when we go to make this parameterization equation, this parametric equation, we'd start with 0 to 2 pi for t. But in this case, I think we can probably agree that it's just pi over 4 to 3 pi over 4. Since that was provided to us. That'll be our bound. So if I want to do just the direct attack method on solving one of these line integrals, the next thing I would do would be probably to find dr, which is just the derivative of r of t. So let's just call it r prime of t. And it's going to be negative sine t, cosine t. And then I could take the dot product with my field and evaluate it from there. Right. I can plug stuff in and just calculate a line integral directly. I think that's not a bad path. But on a hunch, before I get into the weeds of actually evaluating that integral, there is one last theorem that might apply. And that would be the fundamental theorem for line integrals. Right, if we head back up to that fundamental theorem, as long as the field that we're integrating is the gradient of some scalar function, right? Gradient f there. As long as the thing that we're trying to integrate is the gradient of some other scalar function, I can just go back to like the usual way of evaluating an integral, which was f of b minus f of a. So maybe I'll try that first. Check to see if this thing is conservative. Conservative, check. And I think on the formula sheet, there is even a section that'll say specifically what a conservative field means. It's that if f is equal to grad f. I think it says something like that on whether something is conservative. Or maybe the formula sheet tells us that curl f is equal to 0. Might even say both. I don't remember exactly what's on the formula sheet, but it'll tell us something like that. So all we need to do is check the curl, which for this two-dimensional field right here means that I want to check to see if qx is equal to py. Q partial x, see if that's equal to p partial y. Now q is x, and x partial x is 1. And p is y, so p partial y is also 1. Which means that this field is conservative. Right, there is some scalar function that I could find whose gradient is equal to yx. And maybe you've spotted it already. F can be just the function xy. Quick inspection, if I take the partial of x of that field, right, if I look back to just get gradient, which means starting with partial x. Actually, let me move this guy back to gray because we're just sort of checking things here. Xy partial x is y, and xy partial y is x. So that takes us back to the field that we started with, the field yx. Perhaps a more formulaic way of arriving at that answer would be that I could integrate y dx and get xy plus c. Let's just add that in. I'd also integrate the other side, integrate x dy, and get xy plus another c, maybe call it c1 and c2. So when I try to reconstruct that original function, I just need to pick out each unique term I see from these two integrals, And this one was a pretty simple one. It only has the single term xy. Nothing else fancy to it. But since I did find that this thing was a conservative vector field, I can use that fundamental theorem to say that the integral of yx dr is just equal to f of, what'll this be? This will be r of 3 pi over 4, f of r of 3 pi over 4 minus f of r of pi over 4. Color code those things back in for the two angles that we were originally looking at. So I just need to plug in those values. So f of 3 pi over 4. Our function f is x times y. Our parametric curve was cosine t sine t. So I need cosine of 3 pi over 4 times sine of 3 pi over 4, which is going to be negative root 2 over 2 times positive root 2 over 2. Little guy here, big guy there. Minus, same thing, but plugging in pi over 4. That's going to be positive root 2 over 2 times positive root 2 over 2. They're both positive in the first quadrant. Mark off specifically where those two things are coming from. And then I could leave the answer here, though I think this one will simplify nicely. Let's see, if I multiply root 2 over 2 by itself, I'm going to get 1/2, since square root of 2 over 2 is the square root of 1/2. So this is negative 1/2 minus positive 1/2, which is just negative 1. So I think that's probably the easiest method for integrating this particular guy. Though just as an added side to that, if you integrated the line integral directly, I don't think it's going to be too bad. You just go from pi over 4 to 3 pi over 4 of, this would be sine t cosine t dotted with negative sine t cosine t dt. And then you've got a couple of things to integrate. It looks like it'll be cosine squared minus sine squared, which has a trigonometric identity that you'd need to remember. I'm pretty sure that cosine squared minus sine squared is cosine of 2 theta. Yeah, I think that's what it works out to. So you could just integrate that and get to a result. But again, I think the fundamental theorem was an easier option, so I went that way. This particular example, though, that one's not too bad. But I think I'm pointing that out mostly because if we get to the next one, doing it the wrong way will be kind of rough. So when you see these integral problems, it's worth taking a moment, right, when you see them, to figure out what theorem would apply best. So we have some boundary curve, or some curve C. We don't yet know it's a boundary curve. But C is going to be the triangle with the vertices provided here, 0, 0, 0, 4, 0, 0, and 1, 3, 3, oriented counterclockwise when viewed from above. And we want to compute the integral that we see right there. Cool. So, and it also is going to give us a hint. The plane containing the triangles in z equals y. We might come back to that in a minute. So, what's going on here? I see that C is a triangle, and it's a full triangle, right? It's going all the way around. It connects all three vertices, meaning the curve that we're going to try to integrate here is a closed loop. So C is a closed loop. I also see that it's a closed loop in all three dimensions. Let's call it a closed loop in 3D. And it also is given an orientation, nicely oriented counterclockwise when viewed from above. So with all that in mind, I am thinking Stokes' theorem probably applies. We have a closed loop. If we had a closed loop in only two dimensions, we'd probably go to Green's theorem instead. But a closed loop in three dimensions, Stokes' theorem is probably a good bet. So we should maybe look at that formula and see if things will start working for us. So I'm going to go to the formula sheet and grab Stokes' theorem, which Stokes' theorem should be right here in 16a. Yep, there it is. Scroll back up to the spot where it's stated. Yeah, that'll do. Again, you'll have this on the formula sheet. I'm just copying and pasting it from my notes in order to get there. So paste Stokes' theorem. Cool. Here it is. It says that the closed loop inline integral along the boundary of a region is equal to the curl of that field dotted with the unit normal vector and then the surface integral of that. That's Stokes' theorem. So we would need a couple of things if we wanted to approach it that way. Let's see, what are we going to want? We'll need a normal vector. We'll need to figure out our unit normal vector. We're also going to want the curl of our field. So let's split the problem into those two segments. We'll find a curl, or maybe first we'll figure out what our field is, then find the curl of that field, and then also go figure out a normal vector. So what do we want? The field. Let's figure out what that is first. So I think that our field is 4y, 5x, e to the z plus 8. Since to pick those elements out, I'm just going to look within my integral, or looking at my integrand. The nicest way for the integrand to be presented is to just have it already as a field dot with probably dr is the thing that would come after that. But this particular integrand has already had that dot product happen. It's already had the field dotted with dr out into its scalar components instead of leaving it compressed as the two vector components. So we just have to break down those three parts by looking at dx, dy, and dz, which is the traditional way for those elements to be separated. But again, I'll pick out p, q, and r based on what's attached to each of the three differentials. So I think that'll be our field. And then I want to find the curl of said field. So curl F is going to be a set of values. In the curl, P, Q, and R go in reverse alphabetical order. So R, Q, P, R, Q, P. Hopefully I don't need all that space later. They get some partial derivatives attached to them. X, Y, and Z will go in forward alphabetical order, but make sure that none of the similar elements get matched up. So this is going to start R partial Y, Q partial Z, P partial Z, R partial X, Q partial X, P partial Y. Negative, comma, negative, comma, negative. That's our curl. So then we just need to go find values for each of those three elements. So e to the z plus 8 partial y is 0. Minus q 5x partial z is also 0. P partial z, so 4y partial z is 0. E to the z plus 8 partial x is also 0. 5x partial x is 5. And 4y partial y is 4. So there's our curl. Got that from the yellow guy and that one from the purple guy. I think I am going to want that extra space. I'm going to just condense that a little bit. Our curl comes out really nice. It's just 0, 0, 1. Next up, we need a normal vector. So, couple of options. One option for finding that normal vector is to say it is the gradient of the boundary function. We haven't used little f yet, so I think we can use little f. Gradient little f, where f is going to be the plane that those points are contained in. So f is going to be negative y plus z equals 0. Since in order to get the gradient to work correctly, you need to have that boundary function equal to a constant value. And then taking the gradient of that, we get 0, negative 1, 1. We want it to be oriented correctly, which means the z component should be positive, right? If we scroll back up to our surface or to our curve, it's the connection of those 3 points in a triangle viewed counterclockwise and looked at from above. So if you use the right hand rule, curl your fingers around that stuff. This correct orientation should point up, or positive orientation should point up. So I'd end up with that normal vector from the gradient. You could also arrive at this normal vector by just recognizing that our surface is a plane and saying we know how to collect the normal vector of a plane. It's just the coefficients on each of x, y, and z. But remember that all those terms need to be grouped on one side before I pull the normal vector off. And also note that you could have gotten 0, 1, negative 1 instead. Also would be a valid normal vector. It would just have the incorrect orientation. Right? 0, 1, negative 1, still a normal vector, but points in the negative orientation. Since I'm going over all the options, the third option would be just negative g partial x, negative g partial y, 1. Right, for explicit functions, we also have this formula for the normal vector, where g then gets to be the function z equals g of x and y, which is just y. Again, that's where this hint is coming into play. So that's going to be 0, negative 1, 1. So 3 different methods for coming up with that normal vector, all of which are valid. So go with the one that feels best to you. Again, we've looked at normal vectors a lot of different ways. In the end, just make sure that you get 0, negative 1, 1. So, time for Stokes' theorem. we wanted the surface integral of the curl of f, which is going to be 0, 0, 1, dotted with 0, -1, 1. This is now dA, because we've converted over to an explicit function, which means we'll change our our integration region to D instead of S, because we'll now look at the projection of our surface down into the XY plane. Since again, we found an explicit surface, so we're projecting down the Z-axis into the XY plane. Conveniently, this now double integral is very, very nice looking. It is just the double integral of 1 dA over the region D. Which means we just need the area of that region, and we're done. So let's go figure out what our region looks like. So if I project this thing down into the XY plane, ooh, stop that. I wanted to go here to here to here, something like that, and here to here to here, I think. Good enough. Let's try to make that more or less flat down the bottom. Nah, it's good enough. So if I'm projecting my points down into the XY plane, these 3 points are going to be at 0, 0, 4, 0, and what I think was 1, 3, but I should double check that. Yeah. Right, so we come back up to our 3 points. The very nice projection into the XY plane is just to chop off the Z component, and we'll see that projection. So 0, 0, 0 projects to just 0, 0, 4, 0, 0 projects to just 4, 0, and 1, 3, 3 projects to 1, 3. So that's our region of integration. Let's maybe pop color on there. We'll put you in blue. D is this region. And the area of that triangle is just 1/2 base times height. So 1/2 of the base, which is 4, times the height, which is 3. So 6. And we're done. Cool. So to recap, I looked at this thing, saw that we had a closed loop. So I started thinking about either Stokes' theorem or Green's theorem. It seems like one of those would probably apply. We were in 3 dimensions, so Stokes' theorem was the better option. To evaluate that surface integral, I just needed 2 pieces. I needed the curl of f, and then I also needed the normal vector. Since we had an explicit function, I just needed a normal vector whose z component was 1 in order to be oriented positively. If I needed it negative, I would take -1 instead. But got my curl, got my normal vector, and then just took the double integral of their dot product, which we were able to evaluate geometrically. Trying to solve that integral directly is a giant pain, right? If you don't use Stokes' theorem, you need to split up this triangle into its 3 sides. Make sure you orient each side correctly, parameterize each of the 3 sides, and then integrate each of those 3 things. It'll be rather time-consuming and a bit of a headache. So I think that even with Stokes' theorem being a bit challenging, it was the better option in this particular case. Okay, next up, find the surface area of the part of the cone z squared equals x squared plus y squared, which lies above the xy plane and below z equals 1. So to get a really rough sketch of what this thing's going to be, Ooh, that's a rather rough looking diagram. I think that broadly speaking, that's gonna be our surface. This top piece is gonna be z equals 1. This piece on the bottom, it's a cone. Oh, it's a cone. Why did I make it curved? This cone is going to be z squared equals x squared plus y squared. And we're above the xy plane, so I'll just cut it at its vertex because it'll be above the xy plane. So that's the surface that we're after. We do have a boundary of the surface that is a closed loop. So maybe I'd start thinking about Stokes' theorem here, because again, closed loop makes me think possibly Stokes' theorem could apply. But we don't have an orientation, though we could get one if we needed to. But the real issue with trying to apply Stokes' theorem here is that if we're going to start from the surface integral side, we would need the curl of a vector field. And we don't really have the curl in this particular problem, right? We're looking to get the surface area of something, which if we head back to our formula sheet, I believe we'll find that the surface area is equal to just the surface integral of 1 ds. That's our surface area formula. Doesn't exactly mesh well with Stokes' theorem. So even though I've got a closed loop boundary curve here, I'm thinking probably just solving this one straight up is better. So we can head to the explicit formula uh, for a surface area, which says that we need g partial x squared plus g partial y squared plus 1 dA over some area, some flat region of integration, where we just need g being a function of x and y and equal to z. So for our purposes, z can be the function g of x and y, which is the positive square root of x squared plus y squared. I think that'll work for us. So let's just get some derivatives there. They're going to look rather nicely symmetric. So g partial x is going to be 1/2 times x squared plus y squared to the negative 1/2 times 2x. Product rule, I think, should bring that out. G partial y, then, is going to look very, very similar. G partial y will also be 1/2 x squared plus y squared. That thing to the negative 1/2 multiplied by 2y at the end, thanks to the chain rule. Now I think we just need to plug that stuff into the square roots and see what shakes out. So this will be the double integral, still over our region D. We'll figure out what that part is later. I need the square root, so I need the square root of bunch of stuff all mixed up. If I square each of these two pieces, well, first off, notice inside the partial derivatives, there's a factor of 1/2 and a factor of 2. Those things will multiply to 1. So squaring each piece means I'm going to get x squared times x squared plus y squared to the negative 1. Plus, I'll get a y squared times x squared plus y squared to the negative 1 plus 1 and then times dA. Shrink that just slightly. dA. And at first glance, this looks really, really terrible to integrate. Fortunately, I don't think it'll be that bad. Because we can start to simplify some of these pieces. Simplifying what's on the inside of that square root. My first two terms both have a denominator of x squared plus y squared. Square root top a little bit more horizontal. Right, that x squared plus y squared to the negative 1 just means a denominator of x squared plus y squared. And the first term is x squared plus the second term was y squared. It does indeed. Then I want to just pay attention to this plus 1 for a second. Mark it off in a bonus color. Because now I want to add that 1 in. But I'd like to have a common denominator so I can simplify these two terms. The common denominator here is x squared plus y squared. So 1 should be x squared plus y squared over x squared plus y squared. And I'm realizing right now I didn't even need to do that at all, did I? Yeah, that was just for fun since I've been teaching an algebra class. I could have just left that as 1 since the fraction on the left side, x squared plus y squared over x squared plus y squared, that thing should reduce just down to 1. Meaning I could have said that this square root was 1 plus 1 instead of needing to change to a common denominator. Brain must have been elsewhere on that problem. Either way, I think that we should end up with the double integral of the square root of 2 dA. Right, that whole thing on the inside is going to simplify to just 2. So I have square root of 2 times another double integral of dA, which we know is just the area of our region. And in our case, the region is a circle. And it has a radius of 1. So square root 2 times pi times 1 squared is just pi root 2. But if we look back up at our region of integration, we've got the cone that we drew right at the beginning. The projection of that thing down into the xy plane is just going to be the circle x squared plus y squared equals 1. Since we'll be intersecting the cone with the plane, z equals 1. And one more. Compute this surface integral of f dot ds, where f is a vector field, ds is the vector field, or the vector quantity for ds. F is the field that's provided, x, z, y. And S is the surface of the cube, defined by each of x, y, and z being between 0 and 1 with outward orientation. So, what do I notice on this one? Well, the surface that we're being asked to do the surface integral of is the surface of a solid cube. So S is the boundary surface. Boundary surface of a solid. In particular, it's a solid cube, but I'm just going to call it a solid because that's as far as we needed to take it. Another way of saying that means that S is closed. So we could have even added to our notation for that surface integral to put the little circle through that, implying that this is a closed surface integral, and it has positive orientation because that thing is oriented outward. If my surface is closed, if I'm trying to do the surface integral of a closed surface, I should be thinking about the divergence theorem. So I think that that's what I'll do. So I'll scroll over to that formula sheet, which for me means I'm just gonna go back one page in the notes. And go grab the divergence theorem, paste it in, right? I said paste it in right here. Cool. It says all of this. If I want to do that closed surface integral, I could instead just do the triple integral of the divergence. So the divergence of the field that we have, our field is F, or our field F is X, Z, Y. The divergence is just the three, should be just the three partial derivatives in order. So X partial X is 1, plus Z partial Y is 0, plus Y partial Z is 0. So we once again end up with a very nice looking triple integral, going at it the theorem way. So looking at that thing, if I'm just going to do the triple integral of 1 dv, that's going to give me 1 times the volume of our solid, which is 1 times 1 times 1, because it's a cube. So just 1. So applying the theorem, we get something that's very nice, as opposed to if we tried to compute that surface integral directly, I would have 6 different subsurfaces that I would need to parameterize, find normal vectors for, and then integrate those 6 surfaces. Not very ideal. Divergence theorem, way nicer than that. Cool. And somehow I managed to end on time. I can't believe it. Okay, we'll pick up with the second half of this practice exam on Friday. So I'll see you then. Okay, bye, 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 bye.